Hello everyone, welcome you all to this new video lecture. Today we start discussing tuning of PID controllers. So my name is Dr. Bilal Khan and I will explain you how to you can tune your PID controller. So now the first thing is how controller look like. So we have a PID means you have a proportional, integral and derivative control. So it has three terms. One is proportional, second is integral, and third is derivative term. So how this control look like? We have some process here, and before process we implement this controller. And the what we actually do, we have some reference input R of t, and we just want to take the sensor output and compare with the reference, and we generate some error. Now this error goes to the PID controller. Now after manipulation, PID controller will give you some type of actuating input to the process, and that will use to control the system, and the main task is to follow the reference input. So the classical three terms controllers use widely in industry, and if you want to look at, they are used quite a lot right now in a lot of industrial application as well. So what do you mean by PID controller tuning? So it has three terms. One is this proportional that multiply with the input. Input is error. Second one is the gain that multiply with the integration of the error. That's why it's called as the integral term. And the last one is the gain that multiply with the derivative of the error. So that's why it is known as derivative. So it has three terms: proportional, integral, and derivative. So that's why it is called PID. P for proportional, I for integral, D for derivative. Now if I take the Laplace of this m of t, it becomes kp e of s, and similar ki divided by s, e of s plus kd s e of s. Now if I take kp common throughout the relation, then it becomes kp times 1 plus 1 over tis plus tds times error. So here we have three terms. First one we denote by p of s, second one that includes kp times e of s. Similarly, integral includes ki divided by s times e of s, known as I of s. Similarly, for last one is d of s. Now the gain, this gain kp is known as proportional gain. The gain that is multiplied with the integral is known as integral gain, and the gain that is multiplied with the derivative is known as derivative gain. Okay, now when I take the kp outside, so I have some new parameters here, which is denoted by t subscript I, similarly t subscript d, I for integral, d for derivative. So these are known as integral and derivative action times. Okay, so this is basically formulation of PID control, and we will normally look at this where we have Ti and Td times Kp. So we have to look for this relation, and you consider this to solve our problem. But you can use this, there is nothing difference between them. Now again, what is proportional action? Proportional action means that is also known as P mode. It means that it adjusts the controller output according to the size of the error. Okay. Similarly, integral action I mode can eliminate the steady state error. So integral only used when you have a constant steady state error, that is known as steady state offset. So if you have some constant error, then you can introduce integral that will remove that steady state error. Why it remove it? Because when you introduce integral in the system, it will increase the type of the system. So that's why if you have a constant error in previous type, and if your type is moved to higher side, your steady state error is 0. First step input. Similarly, derivative action, which is known as D mode, is actually anticipates the future trend of the error. Okay. Now, to design an effective control system that reduces the adjusting the coefficient of Kp, Ki, Kd, which is referred to as a tuning of control. So, the main idea is that what is controller design or PID tuning? PID tuning means that you have to find the values of these constants. There are three constants. One is proportional constant, then integral constant, then derivative constant. If you want to find or adjust these values, this phenomenon is known as PID tuning. Okay. So to adjusting and finding out the exact values is known as the tuning of the controller. Now, to look at how this controller will work, let's consider the following process transfer function, that is g of s equal to 1 over s plus 1 whole cube. Now, if I introduce a proportional control, that is gp of s equal to k, that is a proportional control, means that if this is my process and this is my gain, I put k here and just give in step input to the system and see how output behaves. So in that case, this is the relation we are getting for different values. Okay, and now what I do actually, I just introduce a gain and just change the values of gain. I put k equal to 1. So this is my reference input. You see that it will start from 0 and the horizontal axis tells us the time and vertical axis is the output. Look here, the y is this is the curve for when I put k equal to 1. Now what happened when I increase the value? Look here, it is more near the reference input. As I further increase it, it will start oscillating, but it is almost reaching the reference input. So when I introduce a proportional control, what it did, it will try to reduce the error, steady state error, but also when I increase the values of gain, there's oscillations coming into the system. Now let's do same system, but here let's assume an proportional integral control, because when we introduce a constant gain we do have a constant error. So look here, when I didn't introduce anything, in that case we have a value of k, gain is 2, but when we start putting the different values of ti, that is the integral gain, look here what happened, it will um, start removing the steady state error with some oscillation as well. So but look here, so the good response is when ti equal to 2, it is not with 1 or 5 or infinity. So the main idea is it is not always the case that when you increase the value you get better response. Okay, so and sometimes your response is degraded when you increase the value. So the main idea is to find the value that will give you the desired result. So we are looking for some optimal solutions. So this is the basic idea that we are looking here for PID tuning. Now the last one is if we want to introduce proportion integral, also derivative. So look here, we assume that ti equal to 2 and k is 3. So when we introduce a derivative term here td, so look here, as I have very small value of td, I do have an oscillation there. Okay, when I increase the value td, that is zero point 0.7, look here, I have very better relation here. Now the main idea was that what we did here, we just plug in different values of these gains, that is k and ti and td. So look here, when I increase the gain of td, I have not a better response, but for td equal to zero point 0.7 I have better response. Otherwise when I increase it further, response is degraded. So the main idea is here is that, so here is the main idea is that it is not necessary that as you increase the values of these parameters you will get the better result. So that's why we need some phenomena, some techniques, so that we can tune the controller. So the basic idea in the industry is, so control engineer will find out the values of these gains. Okay. Now, what we learn from the example that we do here is that the controller gain affects on the dynamics of the closed loop system, that using the KP, KD and KI. Okay, how, for example, we have control terms that is KP, KI, KD. KP for proportional gain, KI for integral, and KD is for derivative gain. So what happens with the rise time? When you have KP, when you increase the values of KP, uh, the rise time is decreases, and when you increase the value of Ki, rise time is also decreases. But when you increase the values of derivative gain, where there is very small change in the rise time. So this means that if you want to improve the rise time, so you have to work on Kp and Ki. Now, similarly for overshoot, when you increase the Kp, overshoot is also increased and Ki also increase. If you want to damp the overshoots, then you have to work with the Kd gain. So it is very obvious because d terms is with the derivative, and it act as a damper to the system to remove the energy. So when you remove the energy, your overshoot is decreasing. So that's why KPKI increase the overshoot, but KD will decrease the overshoot. Or in other words, derivative term actually remove the energy from the system. So that's why a system is converges towards a more stable and less overshoot. So similarly for settling time, so when you increase the KP, there very small change in the settling time, but uh, when you increase the KI, your settling time is also increased. Okay, but for when you increase the KD gain, you have decreased the settling time. Similarly, steady state error. So you can decrease the steady state error by increasing the gain, but you can eliminate it when you introduce the integral term. So the basic idea is integral term is only included when we have a constant steady state error. Then this is the best idea to do it. But there's not much change when you increase or decrease the gain of the derivative term. So this table tell us how these gains behave. That will help us to design the controller. Now, there are some practical implementation issues in PID control tuning, so or implementing the equation. So, first one is that a faithful implementation of the PID equation will not result in a good controller. So, to implement a good controller, it is necessary to consider noise filtering and set point weighting. Why noise filtering? Because if you know that if you have a derivative term in the system, and if you remember that S is equal to sigma plus j omega, so omega is with the frequency, and we know that we have noise at the higher frequency. So as frequency increases, your derivative terms start following the noise. So that's why it's very important to introduce the noise filtering. And for set point weighting, so when you do the integration or derivative, so what happened if you have a constant set point? So what happened in that case, you have a zero derivative term. So that's derivative term is not working. So to avoid this problem, we introduce set point weighting. So now we just look at the derivative gain limitation. So actually differentiation is very sensitive to noise. At higher frequency, noise component is dominant, and it is necessary to limit the high frequency deviation. So as I told you that this S is very sensitive to noise, so we can overcome this thing by introducing a filter here that will low pass filter that will limit high frequency deviation. So this is the ideal derivative one, that is you have KD SEFS or KP TD SEFS. These are two say similar, almost similar implementation. This is the ideal one, but practically how you implement it in the industry, you introduce KP, then you introduce KDS divided by 1 plus KDS divided by N. So N is normally in range of 10 to 20. So this implementation uh, act as a low pass filter to limit the high frequency deviations. Now the next one is set point weighting. So the set point is often constant for a long period of time. The derivative is zero. So the one of the solution is that the set point is often changed in steps. Its derivative is very large. So these are the main problems that we are facing when we have a constant reference. So for these reasons, a derivative part applied on the part of the set points are only on the measurement signal, not output only. So in practical PID, what we do actually, we introduce a gamma time R of S minus Y. So if you have a regulation problem, or sometimes people call it as process control, regulation problem means that you want to approach some point, constant point, or in other words, you want to approach to the equilibrium point. Now, that is your regulation problem. But in process control, we normally have a constant input. So, uh, in that case, what you do, you put gamma equal to 0 so that your variation is with the output. But when gamma equal to 1, you have to put when you have some reference control, or you are working on servo control. Servo control means that you are working for reference tracking. Okay. Now the method that we will use here or discuss today is known as Ziegler-Nichols Tuning method, and the method basically proposed in 1950, and it used a lot. So it will tell us some rules to find out the values of KPTI and TD. Okay, so based on the transient response characteristics of the plant. Okay, how there are two actually methods, ZN Ziegler's method, that can be used. These depend upon the plant dynamic characteristics. Now let's consider first method, that is also known as open loop tuning. So what happened in open looping, what you do actually, if a step input is applied to the plant and the response does not involve either integral or complex poles, then the response to a unit step can be often be approximated first order plus a delay. So this is the basic idea. We approximate our system either in first order or in second order. Now this type of system we can approximate as a first order system. When we do that, we say that okay, it can be represented by sub first order dynamics that has a gain k with a delay minus SL and 1 plus TFS. What do you mean by delay? Delay means that this is the point, this is the time where you apply the input but you are not getting any output. It's known as delay time, and it is represented by N. That is start from this point till that. Okay, now you draw a tangent line to this curve. When you draw it, it will cross a single point and cross the output, reference output. Okay, now what you do actually, this is also known as slope R. So what you do, you start from the activation point, not the delay point, activation point, till where this line, this tangent line cross the maximum value of your output. So you call it as a TP time. This time is known as TP time, and then you will calculate the height of the what you say output, that is represented by K. So based on these, when you find this TP, K and L, now based on these you have to fill in this table, and you will easily tune the controller. So Zn suggests to set KP, KTI according to final table. So how table look like if you want to design a P controller. So you have a Kp and that is equal to T by L, and Ti in that case is infinity, Td equal to 0. Similarly, for Pi case, you have to multiply by zero point 0.9 T by L and L divided by zero point 0.3 and 0 for Td. Similarly, for PID, you have 1.2 T divided by L and 2L and zero point 0.5 L. So this is the way you can easily tune your controller, that is P, PI and PID. Note, note that this results in a PID controller, this one, with a pole at the origin and a double zeros at s equal to minus l. So the main idea is this is tuning is done in that way. Now the second method is known as closed loop or frequency response tuning. So what you do here, you actually first set your integral action equal to infinity and derivative action equal to 0. You just increase Kp in the system, or just increase the proportion gain from 0 until the closed loop system first exhibit sustained oscillations. Now record this gain, which gives you sustained oscillation and the period of the oscillation, that is PCR. Now then select the values of the control according to final table. So you have to use that table and that's it. So table says that type of control is P, PI and PID. So for Kp you have to multiply half of KCR, infinity and 0. Similarly for PI you have 0.45 and then PCR divided by 1.2. And similarly last one PID has zero point 0.6 times KCR, zero point 0.5 times PCR and 0.125 times PCR. So this is the way you can tune your controller. So this results in a PID controller with a pole at the origin and double zeros at s equal to minus 4 by PCR. Now let's consider an example. We have a control system with a negative unity feedback, has a process transfer function that is 64 divided by s cube plus 14s square plus 56x plus 64. Using the second Ziegler-Nichols tuning procedure, that is ZN tuning method, frequency response method. Okay. Determine the value of parameter, that is Kp, Kd, Ki for a PID controller of the form this. Now this is the basic question we have to answer. Now what you do, first of all, determine the closed loop transfer function. Now this is my closed loop transfer function. Now from this characteristic equation you can use root locus to find out the KCR R and PCR. Or in other words, you just denominator put s equal to j omega. Now after doing that, you come up with this thing, j omega CR times 556x minus omega CR square plus 64 1 plus KCR minus 14 omega CR square. So from here, if you solve it, you can easily calculate the value of omega CR. Now omega CR becomes under root 56, that is 7.483. Similarly for KCR, what you have to do, you just plug in the value of omega CR in this equation. Now when you do that, the first term goes to 0. Now you have left with these two terms. When you rearrange them, it becomes uh, KCR is equal to 14 times 56 minus 64 divided by 64. When you solve it, it becomes 11.25. Now similarly for PCR, PCR is equal to 2 pi by omega CR. So omega CR we already calculated, that is 7.483, and just you plug in the values, it becomes 8.8397. Now now I use the table, and from table I know that Kb is 5.63. um, TI for PI controller Kp is 5.06, TI is equal to 0.697. Similarly PID you have Kp, that is 6.75 and 0.420 and 0.105. So this is the way you can easily tune the control. Now here I will stop it, and this is the way you can do the tuning using ZN method. Now in next video I will start discussing how you can tune controller using analytical methods. Thank you.